तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the measurement of velocity of either gases or liquids, and we already looked at the Pitot tube and the pitostatic tube, and we have seen how the principles behind the operation of these. And what we will do in this lecture is to continue with that discussion. I will be taking a simple example of pitostatic velocity measurement in incompressible flow. In the last lecture, I did not explicitly mention anything about the nature of the flow, and in this lecture I am going to talk about it a little more in detail. And the example 28 will indicate how a pitostatic tube can be used for measurement of velocity, and then it will also show what is the effect of compressibility. Compressibility is the effect of change in the density of the medium, which will affect the performance of the pitostatic tube. In other words, the formula we developed earlier would have to be modified to suit when the compressibility effect becomes important. As a sequel to this, I will also be looking at impact probes for high speed flows. When the speed of the medium is more than the speed of sound in the medium, we call it high speed flow. In fact, it could be also very high speed. That means that the ratio of the speed of the medium to the speed of sound in the medium, if it is more than 1, we will call it a supersonic flow. Okay. And if it is very much large compared to 1, it will be called hypersonic, supersonic, and then subsequently hypersonic flow. These are flows which occur in aeronautics and in mechanical engineering in general, and therefore we will look at these things also to some extent. So, if I look at the things we discussed in the last lecture, we discussed the operation of the Pitot tube, and we mentioned that it is based on fluid flow principles. Basically, the fluid flow principles involve the equations of fluid mechanics, the equation of continuity and the equation of momentum, and we did not go into great detail because in fluid mechanics the students would have covered this part of a discussion on fluid flow principles. So, based on the fluid flow principles in lecture 26, we presented the basic relationship between the velocity and the pressure difference measured by the pitostatic tube. If you recall, the pressure at the entry to the pitostatic tube is higher than the pressure, the static pressure, and the difference between the two is measured in terms of a column of a length hm. Hm is the manometric column hm, rho m is the density of the manometer fluid, rho infinity in this case is the density of the medium in which the measurement is being made, and g is the acceleration due to gravity. And we said that the velocity which is inferred from the pitostatic measurement is equal to a constant c, which is to take into account the effect of viscosity and so on. So, we have a constant c which is very close to unity, and in most cases we need not worry about it, multiplied by square root of the density of the manometric liquid multiplied by the g multiplied by hm. This gives you the delta p. Rho m g hm is delta p in pascals or kilopascals, in other words SI units, divided by the density of the medium in which the measurement is being made. The square root of that is going to give you the velocity. We did not really talk about rho infinity in great detail. Tacitly we assume that the density of the medium fluid is constant. So, just let us see when this assumption is valid. The assumption of constant density is valid strictly in the case of liquid flows. So, we say that incompressible flow assumption is valid for most liquid flows. Of course, when the temperature does not vary too much within the flowing medium, then we can say incompressible or constant density assumption is all right. Also, in the case of gases, incompressible flow assumption is valid if the flow velocity u is much smaller than the speed of sound a. A is the speed of sound, u is the speed of the medium. If this ratio, if the value of u is very small very small compared to a, the ratio m equal to u by a, m is the Mach number, it will be small. If the Mach number is small, then we can say that the incompressible flow assumption is also valid in the case of gases. In practice, let us see what kind of flows we have. In the case of liquid flows, liquids may be flowing with a few meters per second velocity at the most in most applications, and the speed of sound in a liquid is really very high. It is in fact given by the square root of the bulk modulus of the medium divided by the density, and typically for a medium like water, the speed of sound will be maybe more than a kilometer per second, and the speed with which the fluid is going to flow in tubes or in ducts, which are the kind of situations we meet with in practice, the velocity may be a few meters per second, and therefore, the ratio of the velocity of the medium to the velocity of sound in the medium is very, very small, and therefore, in liquid flows most of the time we do not even talk about high speed flows. We only talk about incompressible flow in liquids. In the case of gases, however, the speeds can be very high. In aerospace applications, for example, the velocity of the medium related to the, for example, velocity of aircraft, it could be equal to, less than, equal to, or more than the speed of sound in the medium, and therefore, we do have situations where the Mach number can be large enough so that we cannot make the constant density or incompressible flow assumption cannot be valid. So, generally the density variations are expected to be important if the Mach number is roughly little more than about 0.3. So, the formula which we derived in the last lecture is strictly valid for very low velocity or very small Mach number, if we are going to use the formula in the case of gases. So, with this background, let us look at a simple typical example where a pitot tube is being used to measure the velocity of an aircraft. The airstream is at a temperature of 5 degrees and it is at a pressure of 90 kilopascals as measured by an instrument carried on the aircraft, and we want to know what is the aircraft velocity in kilometer per hour if the differential pressure developed by a pitot tube is 450 millimeters of water column. So, what I am going to do is this: take this example 28, work it out on the board, and then look at the whether the incompressible flow assumption is valid or not, and what kind of corrections we have to use, and so on. These are the things we are going to talk about. So, let me go to the board and look at this example 28. So, the data which is specified in the problem I will write down so that we can keep it as a reference here for our purpose. The pressure of the ambient, I will call it as PS, or the static pressure, as 90 kilopascals, 90 into 10 to the power of 3 pascals. The temperature of the air through which the aircraft is moving is given to be at 5 degrees Celsius, and I will convert it to Kelvin by adding 273 to that. So, that becomes 278 Kelvin. The pressure difference which is measured by the pitot-static tube, I will put it here as delta P is 450 millimeters of water, that is what is been given, and of course, I cannot use the pressure in millimeters of water, I have to convert it to SI units. So, let me assume that the manometer fluid has a density of 1000 kg per cubic meter. This is for water, for lack of any other specification. The problem I will take it as 1000, which is good enough for the present purpose. So, we can calculate the delta P in SI units by taking it as rho m g. Actually, this delta P which is given is h m. So, this will be 1000 multiplied by 9.81 multiplied by 450 millimeters will be 0.45 meters of water column. So, this will be in pascals, and if you calculate the value, it comes to 4413 pascals. That is the pressure developed by the pitot-static tube. So, this is the pitot-static pressure. Difference. All right. Now, I will calculate, assuming incompressible flow assumption, assuming that the flow is incompressible. Of course, we do not know whether it is a good approximation or a good assumption or not. We will make the assumption first and then calculate and find out whether it is a good enough assumption or not, and then we will try to recalculate if necessary. So, if you do that, let us calculate the density rho infinity, or if you want you can call it as rho s. I will be using the equation of state P s equal to P equal to rho r t. So, rho will be P s divided by the gas constant times the temperature, and P s is 90,000 90 kilopascals, 90,000 pascals, divided by R g is 287, already we know this, multiplied by 278. This will give you the density as 1.128 kg per cubic meters. So, we have the density now, and all I am going to do now is to use the formula which we recapitulated in the earlier slide. So, the velocity of the aircraft under the incompressible flow assumption. So, I will just call it V incompressible, and I am also going to assume that the factor C is equal to unity, which is very close to 1. Therefore, I am just going to take it to 1. This will be given by 2 into delta P divided by rho infinity or rho s in this case. All I have to do is to plug in the values, and the problem says that I must calculate the value of the velocity in kilometers per hour. This will give you in meters per second. So, I have to find out what is the velocity in kilometers per hour. So, we will just make a simple calculation, meter per second. 1 meter is 1 over 1000 kilometers, and 1 second is 1 over 3600 hour. So, this will become this will go off with that. So, this will give you 1 meter per second, the same as 3.6 kilometers per hour. So, that is the conversion. So, I will just multiply this by 3.6 to get the speed in kilometer per hour. So, just to indicate the conversion between meter per second is kilometer per hour, is simply a factor 3.6 is to be used. So, if I plug in the values, this will be 3.6 multiplied by 2 into delta p was calculated as 4413 divided by 1.128. This comes to 318.445 kilometers per hour. So, the speed of the aircraft when the pitostatic tube is showing a delta p of 450 millimeters of water is equal to 318.445 kilometers per hour. Now, I want to verify whether the incompressible flow assumption is indeed valid or not. For that, I have to calculate the speed of sound in air, and let us look at the calculation. So, we assume that air is an ideal gas for the present calculation. It is adequate to use this assumption with gamma equal to 1.4. Gamma is nothing but the ratio of specific heats equal to 1.4 for air. And we also know from our thermodynamics that the speed of sound A is equal to square root of gamma times Rg times Ts. You can also write it as gamma p by rho if you want, it is one and the same. And in order to calculate again in kilometers per hour, the speed of sound also I would like to calculate in kilometers per hour, I will multiply by 3.6. So, that consistently everything comes out in the units of kilometers per hour. So, I will take it as 3.6 the square root of 1.4 into 287 is the value of Rg, Ts is 278, already we have got this data, and this comes out to 1203 kilometers per hour. So, if I calculate the Mach number, so the Mach number of the flow, assuming it has been the velocity has been determined by using the incompressible flow assumption. So, this Mach number is not necessarily the correct Mach number. The Mach number is based on the incompressible flow assumption for the determination of velocity. So, this will be u by u incompressible, I will just call it ui instead of writing incompressible completely, divided by a, and this will be the values are 318.445 divided by 1203, and this turns out to be 0.265. So, the value of the Mach number of the aircraft is 0.265. Anything less than 1 is called subsonic. So, 0.265 of course subsonic. Sonic means Mach number equal to 1, but subsonic this is already 0.265, not small, because it is close to what we said something like 0.3. It does not mean that exactly at 0.3 the compressibility is going to come into picture. It is a compressibility will become important gradually. Therefore, possibly even at this value of Mach number the compressibility effect may be important, but we can safely say that compressibility effect may be marginal. So, what I will do is I will first look at this compressibility calculation, and I will find out or we will give formulae for calculating the velocity using compressible formulae, and then we will get back to this problem at a subsequent time. So, what I will do is I will go back to the slide. So, the Mach number in example 28 is such that the compressibility effects may be just becoming important. So, the question now is how are we going to introduce this compressibility effect? For that, let us look at the way we are going to do that. There is a difference between the compressible case and incompressible case. In the case of incompressible flow, if you apply the Bernoulli equation as we did, you get the pressure difference is going to be related to the velocity. So, you see that we were measuring the difference in pressure between the stagnation pressure or the pressure indicated by the Pitot tube minus the static pressure indicated by the tap at the side. So, in the Pitot static tube, we remember there is a hole in the very front which is going to sense the stagnation pressure, and the hole which is on the side of the tube is going to sense the static pressure. So, we were measuring the delta P. However, if I look at the compressible flow case, I have to look at the ratio of the pressures. This is the P sub 0 is called the stagnation pressure. We always use the 0 as the symbol subscript for stagnation pressure, and the P infinity is the pressure, the static pressure. What does it mean? It means that when the velocity of the fluid is brought to 0, how are we going to bring it to 0? If it is brought to 0 by an isentropic process, then the pressure is equal to the stagnation pressure indicated here as P subscript 0. The ratio of this to the P infinity is given by the formula 1 plus gamma minus 1 by 2 m infinity squared whole raised to the power of gamma by gamma minus 1. This expression can actually be derived from gas dynamics principles, and some of you will do it in a course on fluid mechanics when you also look at gas dynamics as a subset of fluid mechanics course. Anyway, it does not matter, even if it is not going to be done, we can just take this formula as a starting point, because there is no point in spending time deriving each of the equations we are going to come across. It is not going to be possible to do that. So, I will just I am giving the formula directly as P naught by P infinity equal to 1 plus gamma minus 1 by 2 into m infinity squared whole raised to the power of gamma by gamma minus 1, where gamma is the ratio of certificates, m is the Mach number, and the stagnation pressure to the static pressure ratio is given by this formula. In fact, you can do the following. Suppose the Mach number is very small, okay. That means, if this factor gamma minus 1 by 2 into m infinity squared, this term is small compared to 1, then I can approximate. So, this binomial can be approximated by two term. So, 1 plus this gamma minus 1 by 2 into m infinity squared multiplied by gamma minus 1 plus etc. So, I am just going to use only two terms in that, and if you do that, you will get P naught by P infinity equal to 1 plus gamma m infinity squared by 2 for small m infinity. If m infinity is small, if this term is small compared to unity, then I can approximate P naught by P infinity by a two term approximation like this. Actually, this expression is this expression when this term is much smaller than 1, and therefore, you get P naught by P infinity equal to 1 plus gamma m infinity by 2. So, if you take this 1 to the other side, P naught by P infinity minus 1. So, let me go to the board and look at what is happening. So, let me look at that formula. So, we had P naught by P infinity equal to 1 plus gamma minus 1 by 2 m infinity squared into gamma by gamma minus 1. I said if it is this term is very small compared to 1, I can approximate it as 1 plus gamma m infinity squared by 2 by taking only 2 terms in the expansion. And now, if you see P naught is nothing but P infinity plus some delta P, which is what we are measuring, the delta P. Therefore, I can say P naught by P infinity minus 1, I am taking 1 to the other side, this will become P naught minus P infinity divided by P infinity, and this will be nothing but delta P by P infinity. Therefore, I can see that delta P is equal to gamma P infinity by 2 into m infinity squared, which is the square of the Mach number. So, I will just write it explicitly, m infinity is u divided by a infinity. The symbol infinity here is used instead of s in the previous example, because infinity is supposed to be represent the approaching stream. So, a infinity again this is square of this u squared by a infinity squared. This a infinity squared is given by square root of gamma p by rho whole squared or gamma p infinity by rho infinity. This is nothing but the square of the speed of sound. It is equal to gamma r g t infinity or gamma p infinity by rho infinity. By using the equation of state, I get that. Therefore, if I substitute this gamma p infinity by rho infinity in this expression, so I will go from here to here. I am substituting a infinity squared in the denominator. This gamma p infinity will cancel with this gamma p infinity. Therefore, I will get half of u squared, gamma is going to go off, rho infinity is going to come here. So, you see that half of rho infinity squared is equal to delta p, or u is equal to, you can see that r u equal to square root of 2 delta p by, and what is this formula we got? It is nothing but the incompressible formula we had earlier. Therefore, you take this expression which is valid for high speed flow or non large values Mach number compared to the 0.3 or whatever we have talked about. When this term is small, it in fact goes to the incompressible formula. So, the compressible effect is taken care by this expression. In the incompressible limit, it is going to give the value which we had earlier. Therefore, what I will do is I will go back to the example which we had taken earlier, and so the velocity compressible, that means that when I take into account the compressible effects into account, I can write in the following form. It is just the same expression I am writing. If you go back to the previous board, I am using this. I am going to write m infinity. M infinity is going to be replaced by u by a infinity, and then I will simplify it, and what I get is the expression which I am writing now. It will be square root of 2 gamma p by rho multiplied by p naught by p infinity will become 1 plus delta p by whole raised to the power of gamma minus 1 by gamma minus 1 whole thing divided by gamma minus 1 multiplied again by 3.6 to convert the velocity to kilometers per hour. So, all I have to do is to substitute the values, which I can do. Gamma is 1.4, P infinity is 90 kilopascals, rho is 1.184 and so on. I will not show the intermediate steps. This will come to 315.72 kilometers per hour. So, you compare with the Vi, the previous value was 318.445. So, this is the value you get by using the compressible flow formula. Actually, there is no particular reason why you should use the approximate formula. You could use this any time, because the amount of calculation required is very small. But only the catch is when you are measuring the delta P, you see here that you require all the other quantities also. You have to calculate a whole lot of quantities have to be calculated here. The calculation is slightly more involved, but it is not a big thing. You know all the values, you just plug it in there and get the value. So, the actual velocity, assuming that the formula, correct formula is used, is 315.72. So, you see that you are making 315.7, this is 318.4. You can see that you are measuring, you are making a small error. So, we can calculate the error. This is 72, this is 318.4, about 2.7 kilometers per hour is the error. Actually, the error is positive. If I use this value, I am getting a value of the velocity 2.7 kilometers per hour more than the actual velocity of the aircraft. Of course, in the case of an aircraft, this velocity error may be important, because you are traveling fast, you are assuming that you are traveling faster than you actually are, and you may make a mistake. So, in the case of the aircraft, this may be an important thing, but if you are doing some laboratory experiment and so on, it may still not be a very substantial error. Actually, I can calculate the Mach number based on this velocity. So, I will call it as MC, that will be 315.72 divided by 1203, which was the velocity of sound, and this comes to 0.262. And if you compare with the incompressible one, 0.265. So, there is a small error in the Mach number. So, this may be important in an application of the typical application we talked about. It may be important to consider this. So, with this background, let us now look at the use of Pitot static tube or the equivalent of that in the case of high speed flow. Let us look at what high speed flows are. Before that, I just made a plot here to show the difference between incompressible and compressible assumptions, and I have plotted the two results, incompressible and compressible, as a function of Mach number. And you see that the pressure ratio shows a departure between the two, starting about somewhere here, it will start branching out. You can see that there is a departure from that. The compressible flow assumption for compressible flow case is here, and the incompressible case is at the bottom here. Another way of plotting that, to bring out the difference, more amplify the difference between the two, I take the percentage change between the two values and I place the value here. Percentage change is given by this difference between the two. So, you see that about 0.3, if you remember I was talking about 0.3, you see it is just taking off. It is a small error, and it could be as much as about 8% or more than 8%, about 10% as we reach a value of Mach number equal to 1. In fact, most modern aircraft fly around 0.8 or more Mach number, it may be the compressibility effects are going to be important. So, let us look at the use of an impact probe to measure the velocity of high speed stream of gas. So, when you look at the impact probe is nothing but the pedostatic tube. This tube which is shown here has got a hole at the front here, and the difference between the subsonic or the low speed case and the high speed case is the change in the structure of the flow in the vicinity of the impact probe. So, let us look at the stream coming in is at a Mach number of m1, which is greater than 1, because I am talking about supersonic flow now, and the pressure is Ps, is the static pressure of the stream of air. Mostly we are going to look at air, and this is at a pressure Ps and Mach number greater than 1. And if you recall, at the stagnation point the velocity is actually equal to 0. At this point the velocity has to become 0. That means that the Mach number which is greater than 1 has to become Mach number less than 1, and then it continuously reduces from there onwards to the 0 value at the stagnation point. Okay. Therefore, there are two things. One is the Mach number must, which is supersonic, will have to become subsonic, m2 less than 1, and then it has to stagnate, come to the stagnation here at the stagnation point right in the front of the impact probe. This is what the requirement is. We will not be going into the great details of how things are to be done. We will just borrow information available from gas dynamic literature, books on gas dynamics, and we are just going to look at some of the things from the point of view of application to the case of measurement of high speed flow. It is observed from the appropriate gas dynamic literature that in front of the impact probe, somewhere ahead of it, there is a what I am showing is a shock, bow shock, a curved shock which is going to be present. What is the shock? In the region ahead of the shock, the flow is largely isentropic. The flow subsequently after the shock is also isentropic, but across the shock there is a non-isentropic change in the Mach number from a value higher than 1 to a value less than 1. So, there is a change from supersonic flow to subsonic flow across the shock, and of course, the pressure also changes from value of Ps to P2. So, if I look at the shock which is shown by this curved line, actually it is a surface, and look at the region very close to this point which is shown here, it appears as though it is normal to the stream which is coming in. So, at this location very close to the axis of the impact probe, the stream is actually normal to the shock. So, we can use what are called normal shock relations and relate the values of Mach number, pressure, temperature, density, etc. upstream of the shock to the values downstream of the shock by using normal shock theory, and I will be able to actually calculate the value of m2 given the value of m1. So, that is the first calculation, or I can calculate the P2 given the value of Ps. If I know the Ps, if I know the m1, I will be able to calculate the m2 and P2. Now, between the point downstream of the shock and the stagnation point, I am going to use the isentropic stagnation process, which was actually the formula was given earlier. That formula is going to be used. Therefore, I am going to relate the conditions here to the conditions here through a combination of a shock process and an isentropic process subsequently. Okay. So, the sketch clearly indicates that the stagnation point, the temperature, the pressure is P subscript 02, the upstream of the shock, the pressure is Ps, Mach number is M1. In fact, I am not interested in M2 or even P2, I am interested only in finding out is there a relationship between the Mach number here and the pressure PO2 and the Ps, that is all what I am interested in. For achieving that, I have to measure of course the static pressure here, I have to measure the stagnation pressure P02, which is indicated by the impact probe, and I should be able to find out the appropriate expression which gives the value. So, in fact, we can show from gas dynamics that the ratio of the stagnation pressure P02 to the static pressure upstream of the shock or in the stream which is coming in at a velocity such that the Mach number is M1, the ratio of this pressure is given by this expression. So, it consists of two parts, this is one part and this is the second part, and in fact, the second part is actually due to the isentropic process of stagnation from M2 to the value of 0 at the stagnation point, and this is due to the normal shock relation. So, let me just spell it out, 2 gamma M1 squared over gamma plus 1 minus gamma minus 1 over gamma plus 1, this is the first factor, and the second factor is 1 plus gamma minus 1 by 2 into M2 squared, M2 squared is this value whole raised to the power of gamma by gamma minus 1. So, I have a simple combination of these two, and in fact, you can see if M1 becomes very large, all these factors become unimportant, this is the only factor which is going to survive, and I will get P02 by P S equal to 2 gamma M1 squared by gamma plus 1 as M1 tends to infinity. So, this is the limiting value. So, let me look at the pressure ratio, but here I have plotted the pressure ratio not P02 by Ps, but Ps by P02, reciprocal of the pressure ratio which we measured as a function of the Mach number. I start with a value of 1, 2, 3, 4, 5, etc. So, as we go towards the right here, the stream is becoming high speed stream, supersonic stream, and if you look at this value, it will go to 2 gamma M1 squared by gamma plus 1. You remember the pressure ratio, that will be inverse of that, that will be the value, asymptotically it will reach that value. And the point is, if I measure this ratio Ps by P02, all I have to do is to just read off from here what is the corresponding Mach number. So, actually the impact probe, it is called the impact probe because at the stagnation at the front of the probe, there is an impact, the fluid is going to come to a rest at the front. So, it is called an impact probe because of that. So, in the impact probe, I am going to measure the static pressure in the mean stream which is coming in. I am going to divide it by the pressure indicated by the Pitot tube. So, this ratio is going to be related to the Mach number of the stream. So, you can use a graph of this type to measure. You measure the y axis, whatever is indicated is measured, the x axis gives the corresponding Mach number. If you want, you can plot the Mach number along the y axis and the pressure ratio along the x axis if you feel more comfortable, but essentially the information is contained in this graph. A second type of probe which is used in supersonic streams measuring the Mach number is a wedge probe. So, the first one was a pitostatic tube. In fact, you can put any tube there and it will do the job. It does not even have to have any particular shape like a Pitot tube. It could be even a simple tube itself. Okay? Sometimes it is used like that. A wedge probe, what is the difference between this, the Pitot tube, Pitot probe and this? It is in the form of a wedge. You can see the cross section is a triangle. The stream is coming in this direction and the pressure tap is actually on the side of the flat side. So, there is a flat side here, I am going to have a pressure tap. So, let us look at the wedge probe and how it is going to work out. So, I have shown two sketches here, wedge probe in a subsonic flow at the top and the wedge probe in a supersonic flow at the bottom. And what we notice is that in the case of subsonic flow, the flow is going to have the streamlines are going to be curved like this as is shown here, and a nice streamline flow is going to be the result. But in the case of the same wedge kept in a supersonic stream, you see that starting from the corner there is a oblique shock. The shock is at an angle to the, that is why it is called to the stream which is coming in, and therefore it is called the oblique shock. And what happens is that the stream is going to come like here and just take a change of direction abruptly at the shock wave. The shock is a very thin region where irreversible effects are taking place, like viscosity, heat transfer and so on. They are important within this region. And what happens is that the incoming stream, which is coming as a nice parallel stream, is going to abruptly change its direction by an angle exactly equal to the angle of the wedge, so that the streamlines are parallel to the surface of the wedge. Here they are not necessarily parallel to the wedge surface. You can see that it is coming in slightly curved, and finally it of course it looks like it is parallel to the wedge, but here it occurs abruptly at the oblique shock. In fact, the gas dynamics is going to give us information about how to calculate. I have not shown the bottom. Bottom it will be symmetric. I have an oblique shock. The important factors which we are interested in are the pressure P1, which is the pressure upstream of the oblique shock, P2 is the pressure downstream of the oblique shock. This pressure is what is measured by putting a hole here. If you this hole here is going to measure P2. This P2 is measured by the hole there. So, let us look at the expression for the relationship which is going to be used for measuring the finding out what the Mach number is. P1 is measured, P2 is measured. The angle theta is known because the wedge, we can choose the correct angle for the wedge, whatever may be a few degrees, and the oblique shock is going to be located such that there is an angle of alpha between the stream after it turns and the shock. This angle alpha depends on the Mach number of the stream and the angle theta. So, the alpha is a function of the Mach number of the stream and theta, and P2, P1 are measured, and let us look at the formula which gives me the pressure ratio. Again I am measuring a pressure ratio, not a pressure difference, contrary to what we were doing in subsonic low speed flow. The shock angle alpha itself is a function of m1 and theta. Theta is the angle of the wedge. Table available in books on gas dynamics will give you this relationship. So, if you know what the Mach number is, if you know what the theta is, and then alpha will come out as a function of these two. Suppose I know the Mach number, the pressure ratio P2 by P1 can be shown to be equal to 2 gamma by gamma plus 1 m1 squared sin squared alpha minus gamma minus 1 by gamma plus 1. So, let us look at this formula in some detail. This is the, in the case of measurement, I am going to measure this ratio, I want to find out what is this m1. So, I can rearrange this formula in terms of m1 equal to some function of alpha and P2 by P1. If you want, you can do that, but we will come to that in a little while from now. However, alpha here is also a function of m1 and theta. Therefore, because I do not know what the Mach number is, even though I know theta, I do not know what the alpha is. So, some kind of an iterative scheme is required for calculation, as you can very easily see. So, you can assume some alpha or some value of m1, find out the alpha, put it here, and then find out what is what was the P2 by P1, compare it with what the P2 by P1 from this formula gives, and then if the two are going to agree with each other, then you know that that is the correct value of m1, otherwise you iterate, you take a different value and so on and so forth. So, one has to use an iterative scheme to obtain the Mach number from the pressure ratio. So, pressure ratio is measured, theta is known, we find out what is the Mach number of the stream by using this formula, if necessary by an iterative sort of relationship. I have taken a simple example. For example, if I have a wedge of angle equal to 8 degrees, from the tables in the book on gas dynamics, for a Mach number of 1.5, alpha turns out to be 53 degrees, that is theta is given. I am also given the Mach number, because in this case I want to find out not the Mach number, but the pressure ratio. So, m1 equal to 1.5, alpha turns out to be 53 degrees from the table. Then with gamma equal to 1.5, 4, we can calculate the ratio of the pressure P2 by P1, and that will given by 2 into 1.4 divided by 1.4 plus 1 into 1.5 sin 53 whole squared. This is m1 sin squared, m1 sin alpha whole squared, minus gamma minus 1, 1.4 minus 1 divided by 1.4 plus 1, gamma plus 1, this gives you 1.508. So, if the angle of theta is 8 degrees, and if the incoming stream at a Mach number 1.5, you get a pressure ratio of 1.508. Or working backwards, if you measure a value of 1.508 for the pressure ratio, and if the angle theta is 8 degrees, then the corresponding value of m1 is equal to 1.5. So, you can sort of work backwards and find out what is the Mach number. So, with this basically we have covered both the subsonic and the supersonic case or the high speed case, and let us look at one other matter which also is important. We have not looked at it carefully. So, this is regarding the direction of the flow. So, we were talking only about velocity. What about the direction? Of course, we know that velocity is a vector, and therefore, we will be interested in finding out what the velocity magnitude is and also the direction. I will just briefly touch upon it. Let us look at a simple scheme like this. Suppose I have a tube with a central hole, and let us say I have another hole at the top and another hole at the bottom. So, I have another hole at the bottom. So, this is a 3 holes or 3 hole probe. Let us look at the way it is going to behave. Suppose I look at only low speed flow, I am not interested in high speed flow with the multiple holes, probes and so on, only low speed flow. If the velocity vector is in this direction, if it is in this direction, the pressure, so suppose I take this is 1, this is 2 and this is 3, delta P between 1 and 2, delta P between 1 and 3, if it is exactly coming normal to the probe, these two are going to be equal. Okay. So, delta P equal to delta P 1 3 if V is aligned with hole 1. I am not going into great details, I am just going to give some ideas about how these things work. Suppose the velocity is not in that direction, suppose the velocity vector is in a different direction, let us say it is coming in this direction. Suppose the velocity vector is in that direction, delta P 1 2 will be different from delta P 1 3. Okay. In this case it is symmetric, both the pressure differences are the same. If it is aligned at an angle, let us put it as angle equal to alpha, okay, this is the angle in the plane of the probe. I am assuming that the velocity is coming in the plane. If it is out of plane, again we will come out with similar discussion. So, let us look at the thing. The delta P12 is not equal to delta P1. Actually, what I can do is I can experiment with streams at different angles by orienting the probe in different directions and finding out how this delta P12 and delta P13 behave with respect to angle alpha, and therefore, I will be able to actually use the probe and find out the velocity as well as the direction by using that kind of an information. If the velocity vector is in some arbitrary direction and the probe is oriented again in an arbitrary direction with respect to the flow velocity, you can in fact think in terms of a multiple hole probe, one at the center. For example, I can have a 5 hole probe as shown here. So, we have multiple holes. So, you can see now that this can be called 1, 2, 3, 4, 5. I have 4 different delta P's, 4 in number. So, these will be depending on alpha in this direction, this angle phi, and you can have an angle beta in that direction. That means that the probe can be rotated with respect or at an angle with respect to V as is shown here. It can have an angle alpha in this plane, beta in this plane, and an angle phi like this. So, the delta P's are going to be sensitive to alpha, beta and phi, and we can again calibrate the probe so that the velocity as well as the direction information can come from such measurements. So, this is basically the idea of a multiple hole probe, which is used in many important fluid mechanics applications. I think we will stop here in this lecture. In the subsequent lecture, we are going to look at the measurement of velocity using a hot wire anemometer and also a laser Doppler anemometer. These are also useful for measuring velocity, and that will actually be completing our discussion on the velocity measurement. Thank you.